Welcome, everyone. We're grateful to have you here at our November webinar. I am happy to talk a little bit about what's been going on with our water year. So the water year runs from October through September. It's the way everyone in the United States manages their water. And so I just gave a presentation to the state about our water year. So we're going to have a little bit of assessment on that. And when I'm done with my presentation, we'll have our assessment on what Paul Iniguez, our guest speaker from Scripps, will be able to tell us about what we might expect this winter. So a little bit about what Arizona has been dealing with our water supply. We have been in drought for 30 years. Our office starts our drought as water year 1994. So we have been in drought for 30 years. With drought in Arizona, it's really a series of dry years interspersed by a wet year here and there. And we're fortunate this last water year was actually above the long-term precipitation average. So you can see those numbers down at the bottom. You can see what's happening with our long-term average precipitation. It's about an inch below the long-term precipitation. So we actually did a pretty good thing. For the last 30 years, 20 of those years have been below that long-term average. So they have been dry. When we're looking at where the precipitation for the water year happened, so this is looking at the entire state for the entire year, you can see that most of the precipitation was in the northern tier, so Mojave County, Coconino County, you can see Navajo County and Yavapai County really getting above average precipitation for the water year, but down in Pima County, Cochise County, Santa Cruz County, much below average. And in fact, Cochise County, portions of Santa Cruz County, a little bit of Pima County, really very, very dry for the water year. When we're looking at our temperature for our water year, so this is looking at one number for the entire water year for the entire state, this was actually a cold water year overall. Even though we recall what happened in July and how that impacted not just Arizona, but also the Southwest, overall, our wet and cold winter really held us together with that overall temperature for our water year. You may recall last October, we actually had precipitation last October, and we actually had the 14th coldest November on record for the state last year. You can see this year we're not dealing with that same kind of conditions. But overall, the water year was not that bad when we're looking at temperatures statewide for that entire time frame. But you can see some places were better, some places were warmer for sure. When we're looking at our short-term drought, we can see that there was so much improvement with how wet our winter was, that we had a lot of our short-term drought improve, but then we all remember what happened with our summer monsoon and how it never really came about until August and September. September was actually a normal amount of precipitation for the state, but unfortunately, September is not a very wet month. And so we started degrading with our short-term drought, and you can see how that happened. And what we look at when we're evaluating what's happening with long-term drought is we look at something called the SPEI, which is you can see it down there at the bottom, Standardized Precipitation Evapotranspiration Index. So going back 48 months, that's the chart that you're seeing there, looking at kind of how dry and how thirsty the atmosphere happened to be. So looking at that long-term conditions, you can see that we're still in a deficit. And in fact, if we go back the last 5 previous water years, looking at how much precipitation happened across the state for that water year, you can see most of those years have been deficit years. And of course, then that builds in with our long-term drought. Our long-term drought has persisted. You can see that some of it has changed from the wet winter, but it was amazing to see July and how much that impacted, especially Maricopa County. You can see that extreme long-term drought started building up again. So unfortunately, long-term drought persists. This is where we're at for our water years starting October 1st through November 15th. Unfortunately, very dry and very warm. So it looks like it's not a good start to our water year, but hopefully this event that we're experiencing, we did get 407 inch of precipitation at Phoenix Sky Harbor today. We're thrilled with that. We need a little bit more. And so when we're looking at what's been going on, overall water year 2023, which was the last water year, it ended September 30th, was overall cool and wet. But unfortunately, our drought levels are building, and water year 2024 is starting warm and dry. So that's what we have for our summary. And I'm going to go ahead and introduce our guest speaker. We're thrilled to have our guest speaker, Paul Iniguez. He is a forecast verification analyst for the Center for Western Weather and Water Extremes. That location, everyone should know, those are the world's experts on atmospheric rivers. So we're grateful to have Paul come and talk a little bit about what's going on with the atmospheric rivers. But you may remember Paul from the National Weather Service Phoenix office, the Science Operations Officer. So he'll still be working in Western water, Western conditions. We're really grateful to have him and as our guest speaker today. So I'll go ahead and send it over to you, Paul.
All right. Thanks, Erin. Thank you for the invitation to speak with everyone today. As you said, I'm with SCRIPS, the Center for Western Weather and Water Extremes, which is part of UC San Diego. And I'm going to talk today a bit about what we do. A big part of what we look at in the study is atmospheric rivers, and that will kind of lead into the winter outlook as well. So just kind of looking at the center and what it entails, our director, Marty Ralph, he may be known to some folks in there. He's been in the Southwest for quite a while. There's a couple of big things that we focus on in the center here. The one you see at the top is the forecast-informed reservoir operations. So that's where we are intensely studying how good are the forecasts, and then can we use that forecast information to change how reservoirs are operated? Because it may be kind of surprising to you, but most reservoirs do not use forecast information in their operations. They are simply reactive. They are not proactive. So FIRO aims to change that. So we're working at it with many different watersheds and partners across the West to help do that. Some of the other stuff we do, climate science, you see there the picture of the airplanes. I'll talk a little bit about that, where we do atmospheric river reconnaissance flights. There's a lot of work. Folks are working on seasonal to sub-seasonal type projects, a lot of new machine learning kind of stuff coming online. And as far as forecasting, we do produce a lot of information on our website, a lot of model data folks can look at, but we also do run in-house our own version of the weather research forecast model, the WRF, we call it the West WRF, and even do a 200-member ensemble, kind of the super ensemble, that information is available online. So I mentioned atmospheric rivers, so I'm just going to start playing this short little video from my center that talks a bit about what they are.
A river in the sky with more than twice the water of the Amazon. It's called atmospheric river. Atmospheric rivers are long interval bodies of water vapor that produce major amounts of rainwater. Atmospheric rivers begin in the warm waters of the Pacific, where water evaporates into the air. When this humid air meets a Pacific storm, the water vapor is concentrated and driven toward the coast, becoming a fire of rainfall in the air. Once the atmospheric river reaches the coastal mountains and the inlands the area, the collision squeezes additional rain and snow from the system. Atmospheric rivers are responsible for outflow and precipitation. Some institution ocean developed a new system that rates atmospheric rivers instead from none to 5. The rating system helps identify atmospheric rivers that are beneficial, such as those that replenished reservoirs, ones that produce transits like flooding. Understanding atmospheric rivers is key to improving weather forecasts for better managing water resources and predicting flood risk.
All right, so that a little bit on atmospheric rivers. I may keep my camera off a little bit if it's kind of coming in and out here, we'll see. But so atmospheric rivers are phenomena that occur across the entire planet. You see the map on the left side is showing a frequency, annual frequency of atmospheric rivers. And there's a metric there, it's called IVT, and that's the integrated vapor transport. So that's kind of the way that we measure these atmospheric rivers. It's taking into account how much moisture is present and then how strong the winds are. So you're looking at how much moisture is being pushed through the air. So there's some pretty favorite spots across the northern hemisphere that you see, one across the North Pacific, and then as you get out into the Atlantic off the eastern seaboard, basically. That's main areas that we see that. And then on the right side, all the dots, these are locations where the atmospheric rivers make what we call landfall, so where they are first encountering land masses. So not surprising, it's mostly on the windward side of the major continents, so along the west coast. I mean, right all the way from Alaska further south. So as you get down closer to the equator, you can see that these dots get much smaller because there's much less frequency of the atmospheric rivers when you get down towards the equator, so much more southern latitudes. ARs are a big deal for the western U.S., so it's not just California, Washington, Oregon. They do also play a pretty important role in precipitation for the inland states as well. The map in the center of the image shows what percent of the water year, there's functionally annual rainfall for the West Coast. How much of that is due to atmospheric rivers? So where you see those darker oranges and reds, so that's about 50% or a little bit more so of the annual rainfall is associated with these ARs. If you look down into Arizona, those values range from roughly 25% near the Four Corners, upwards of almost 50%, it looks like, down towards like Yuma area. But if you look at the map on the right side, what the research here is showing is you taking how much rain is coming with those atmospheric rivers, but then looking at how many days of atmospheric river conditions are there. So there's a lot less ARs that end up hitting or penetrating into Arizona. So you can see that that's much more impactful actually in this area. So where you have like these, where the ARs do come in, they tend to bring quite a bit of precipitation to Arizona and the Southwest. So when do these typically happen? The map on the left side is showing different areas and when is the peak for the AR activity, AR landfall. So you can see for all of Arizona, it's basically December or January. So kind of as we're getting into the heart of the winter, that's when we'll see the main ARs that far south. You can see the bar charts are showing the frequency for different locations. So if you compare a place up here off the Oregon coast A, you can see the frequency of ARs they have down there compared to down here near San Diego, quite a bit less there. For in Arizona, I pulled some data, and this is looking at the upper Salt Basin, so just a bit northeast of Phoenix itself, and looking at frequency of the IVT. In the 90th percentile was about 150 units. So these are kind of looking at the IVT or AR conditions for central Arizona. When they come in, they very strongly tend to have a southwest orientation. And we'll look at just a couple of these extreme events that happen here. We'll look at number 1, 3, and 5, because they're all kind of more recent, significant ones. So I'm going to play a bit of a radar loop here. So this is from back in January of 2010. And so in Arizona for a while, they may recall this event. So this was pretty active. We had about 5 days of precipitation. So there were numerous atmospheric rivers that were moving across the state when they culminated in a pretty significant event on January 22nd. So you can watch this radar loop as it plays through. And the schematic you see on the left side was from some research where they looked at this specific case and kind of came up with this idealized model of what does it take for a big AR event in Arizona. And so here on the radar loop, you can see this is kind of really starting to get into it. You see a lot of precipitation starting to show up on the radar. And if you look at how fast the stuff is moving as well, its speed's picking up, so the IVT is increasing. The rain's not stopping here. What ended up happening is that there's communication issues going on, so the radars were actually getting knocked offline because the storm was getting so intense. We can get these big ARs into Arizona if they can kind of they move kind of south and they can kind of shoot through this Baja Gap where there's the terrain, the mountains aren't quite as tall in near the central part of the Baja. So, and then you can get extra moisture kind of flowing up through there, which comes into Arizona. And then of course it starts moving into higher elevation. You get the topographic or orographic effect where it starts raining out the precipitation, and you can get pretty heavy rainfall and snowfall with these events. So here's another event. This was ended up being the strongest IVT for the Salt River domain on record. So this was, you can see what this IVT, what this AR looks like as it was coming in. So The heaviest axis of it was coming south of the border, basically, and then up into Arizona. And this was kind of ahead of a big upper level low pressure system that was more in the Pacific Northwest. If we look at this next event, I'll show you too. So this was right around Christmas time, just a few years ago. So 2 years ago, this was actually the fifth strongest event there. And just grabbing a map around that time, very similar. It had, again, that southwest orientation, and you had the strong IVT kind of coming through the gaps in down in the Baja. And again, looking at the upper level map, very similar pattern. You have the strong upper level low that's more near the Pacific Northwest, and that's really increasing the flow, the winds, and then interacting with moisture that's coming up north from near the tropics. So it's kind of the typical pattern we would see for these really strong atmospheric rivers. Last year was a big year for ARs across the West, and especially California. There was 46 atmospheric rivers that made landfall along the West Coast. At Scripps here at the center, we have created and used this atmospheric river scale. So it kind of rates them from 1 to 5, just like you might think of tornadoes or hurricanes. And we come up with that metric based on how high that IVT value is, but then also looking at the duration. So if you have high IVT values and it also lasts a long time, that means you're going to likely have some pretty serious impacts. So when you get up to that category 4 and category 5, that's more your big flood events that can happen along the West Coast. Let's see. So yeah, so we monitor this stuff, and this is some of the climatology that's there. I'm going to shift a little bit into some of the tools that we use to forecast and look at atmospheric rivers. So I'll promote our website. The URL has been in the top right corner of the presentation, and you can go there. If you look under the forecast tab, there's a lot of maps, a lot of model data that's available in there that we're looking at, daily, routinely, to figure out what the forecast is looking like for atmospheric rivers. So the image, the loop I have on the left, that's a recent forecast. We're just looking at the IVT from one weather model across the Northeast Pacific. So this is something that we look at every day, especially as we're getting into our atmospheric river reconnaissance flights. And I'll talk about that in a moment here. So this is one way for us to look at that and kind of see what the models are predicting as far as IVT across the ocean. Then when you get to actual locations on land, we have different tools like this, like these plume diagrams, which you can pick a location along the coast. And we also have transects that run inland as well. And it shows these plumes of what all these different weather models are forecasting the IVT values to be at this location going forward in time. So this was a forecast from within about 2 days ago, and it was looking at the potential IVT for today, moving through at least across the Baja, and that was going to go into Arizona. So each one of these lines here, all these little gray lines you see in the background, those are all different weather models. So in this instance here, there's about 80, I believe, that are showing up, and we can start drawing statistics from that as well. But this kind of gives us an idea of timing. We can see a lot of the weather models were forecasting an increase in IVT values during this period. It gives us an idea of how intense they might be. So some of these lines were getting as high as 750 units, which is getting into that moderate, maybe even a little bit of the strong category. But we see the majority of them were kind of straddling here in this weak category. Up to about 500 units would be considered weak. So it wasn't necessarily anticipated to be a super strong event. Most of them were showing it kind of this weak event that is going for today. Another popular tool that we have on the website is this AR landfall tool. And it's kind of a little wonky to figure out what you're looking at first, but once you get the hang of it, it's a pretty slick thing. If I look at the map on the right side, we have all these different dots, and there's a dot essentially for every quarter degree as it's running along this transect. And if you just follow this dot straight over to the left, that's going to correspond with the vertical axis here. So it's basically like we took all the dots on this transect and just shoved them all the way to the left, and that's our vertical axis. And then what you see on the horizontal axis, this is time, the forecast time going forward. So if I go all the way to 8, this is going to be 8 days from now. You can see that that's going to be the 22nd. So we have kind of squishing the map here and kind of seeing what is the probability of these AR conditions that the models are forecasting along the coast. So the colors you see are associated with the color bar, and this is what percent of the ensemble of the model data is saying that there's going to be IVT values of at least 150 units in this case. So with this forecast I grabbed here, very high probability here. So this is associated with what's going on right now, where there was a very high chance of these pretty weak, admittedly, IVT values coming in, but very high chances. And then as we go to the left, that's going forward in time, we can see that those probability values sink further and further south. So basically that's showing us that the AR is moving southward as as time is progressing. And then if we look further out in time, there's at least for California and areas inland Arizona, not seeing much of any probability for activity, at least in this model run. And you start getting out here all the way out to 15 or 16 days. So the models do run that far. Of course, when you start getting out that far, they get less and less reliable and accurate, but there's still good information to look at. So this is a great tool that gives you a really quick snapshot of what's going on and what's coming up. And it's something that we use every day in the center. I mentioned that we run our own in-house weather model as well. So we have what's called the West Work. So it runs at a pretty high resolution. The map you see on the left side, that's at a 3-kilometer resolution that's running, and it's specifically tuned. So the physics of the model is specifically tuned to Western weather and specifically atmospheric rivers. Then we also run this ensemble. It's a 9-kilometer ensemble, but we use 200 members, which is huge. The American, the GFS model is currently running at 30 members. The European model is running at 50 members. So we use them and a bunch of other permutations, and we come up with 200 ensemble members. So what you're seeing here is every horizontal line is a different ensemble member that's showing us precipitation over the next several days. So it gives us an idea. If we get many members showing the same thing, that gives us higher confidence of what's going to happen. So a lot of these members, I just grabbed the latest stuff today, are showing a high probability for very light rain this was at Sky Harbor itself. Looking a little bit further out too, there's a lot of work that the center is doing in what's called the seasonal to sub-seasonal time frame. So that's kind of beyond the weather forecast. Weather forecasts right now are generally reliable 7 to 10 days, maybe 14 days sometimes. And this is looking more at this week 2 to week 3 period. This is the latest forecast from one of the weather models. And what we're seeing on the left side, this is looking at the number of AR days that are being forecast by these ensemble members. And then we can compare that to the climatology, which is the model in the bottom center. And then that's giving us what the anomaly is. So this is showing that in the week 3 period from now, that there's an enhanced probability of more AR activity than usual going into central and northern California to Oregon. Not seeing much of a signal, if maybe slightly less for further down in the southwest. So these are just more tools that are available on our website. The other big thing that we're involved in now, especially getting into the winter, is the atmospheric river reconnaissance, the AR recon flights. We are using the same planes, essentially working with the same folks that are the hurricane hunters. So when there's a hurricane tropical system out in the Pacific or the Atlantic, and they're flying out there to do sampling, these are the same planes, the C-130s and the G4, that are flying in there in these atmospheric rivers. So coming up this winter, this is going to be the 6th or 7th year, I believe, that we've been doing this. We're going to have, at the peak in January, there's going to be a window where we're actually going to have 3 planes available to us for this reconnaissance flight. There's one plane that's situated out of Mather in California, that's near Sacramento. Another plane is going to be in Honolulu, and then we're going to have a plane also out in Guam. So we're going to be able to span the Pacific essentially and trying to get information of what's going on out there, because it's maybe not surprising. There's not a ton of weather data out over the Pacific Ocean because you don't have radars all over the place. You don't have weather stations. There's not balloons being launched. Satellite data is what we have for the most part. So these planes are going out there and they're flying these tracks every day. We meet and we work together to come up with what tracks should the planes fly if they're going to go out, if there's targets. So this is an example from a few years ago where there were 3 planes that went out. So you can see the IVT, essentially where the atmospheric river is on the map, and then the black traces are where the planes, their routes were traced out for them to fly. Wherever you see the little black squares, that's where the black squares, the triangles, and the circles, that's where they did drops on. So it's the same thing the hurricane hunters do. They push an instrument out the back of the plane through a little chute, and it falls down to the ocean. As it's falling down, it's recording information, the temperature, the humidity, and it's being tracked with GPS so we can calculate the wind speed, sending that back to the plane, which comes back to us in the center in real time. And then this data goes forward into the weather models and can really improve the accuracy of the weather models, improve the prediction of rainfall and snowfall across the West Coast. So these are really good and important flights, and they're really kind of expanding and pushing the boundaries of our science right now. So let's talk a little bit from atmospheric rivers and transitioning to ENSO, El Nino, La Nina. Just a little quick on what that is. So during typical conditions across the Pacific Ocean, you see this schematic here showing the ocean temperatures, and we typically have a lot of thunderstorm activity near Indonesia, and this drives a lot of the weather across the Pacific. But when we get into an El Nino, if I just go back and forth a little bit, if you look at the shading on the surface of the ocean there, you can see that there's a lot warmer water along the equatorial waters of the Pacific Ocean. And that causes this area of thunderstorms to shift. So instead of being near Indonesia, it's going to be further east. And then that kind of impacts the storm track across the North Pacific, impacts the storm track across North America. So it kind of has this knock-on effect across the Northern Hemisphere and kind of in the globe in some aspects. So when this happens, I didn't show the La Nina, but it's kind of the reverse of that. So instead of warmer than usual, it's colder than usual. And these maps here kind of show the typical, I say typical, expectation we would have for winter in an El Nino or a La Nina. So you can see during an El Nino winter, we typically would expect a bit of wetter conditions along the southern tier of the US, including Arizona. But sometimes it's not a very strong connection, and it doesn't always work out that way, because if it was that simple, the El Nino forecasts are pretty good and the ocean is very slow responding. So if it was a simple switch of yes, no, El Nino means yes, no, wetter than usual, the forecast would be fantastic. But there's all sorts of other stuff that goes on. This was some interesting work I saw that NOAA did on their ENSO blog. Looking on the left side, it's the number of El Nino winters. So out of 29 El Nino winters, how often were they wetter than usual? You can see there's pretty light green shading across Arizona. So maybe a little bit more when you get into the Four Corners, but it's not a tremendous amount. So it's not a lock when you have El Nino conditions that the winter is going to be wetter than usual. And if you look at the temperature on the right side, kind of similar, a little bit tilted towards cooler. More often it's cooler than usual, but it's not a very stark difference that we see. I talk about how does El Nino play into atmospheric rivers? We do see from research that the state of ENSO can impact the frequency of atmospheric rivers across the planet. So if we're looking at El Nino on the right side here, we see that kind of well off the West Coast, off California coast, it can result in more atmospheric rivers, but it doesn't necessarily extend very far inland as well. So, the research does support that there is some modulation of ARs across different parts of the world when you have El Nino, but, for most of the world, it's not an incredibly strong connection. So we can't necessarily say that because we have El Nino conditions this winter that was going to result in more ARs. The science is not there to support that kind of evidence. So when we're making these outlooks, I call back a little bit to last winter. Last winter we had La Nina conditions, pretty decent La Nina conditions, and they had been going on for a while. So typically when we have a La Nina, you would have that drier than usual precipitation across the southern US. And that's what NOAA had put out in their final winter outlook, was that the odds were tilted towards a drier than usual winter. So the map in the top left is showing what the forecast was. And what you see, the bigger map on the right, is that's what happened. We had very wet conditions across California. Arizona was in the top third of wettest winter. So you had this pretty big streak of wetter than usual weather that extended from California well into the upper Midwest. So when we look at these outlooks, and I'll show the latest ones here in a moment, but we really have to remember that they're probabilistic. They're not yes, no binary forecasts. So even last year, there's this shading of brown here that still indicated that there was, so this pie slice here of what's the probability of above normal precipitation was pretty big, but there's still pretty decent chances, especially if you combine the other two, that the probability was more likely it would be near or above normal as opposed to just, or above normal as opposed to just below normal. So we certainly have to think probabilistic probability when we're looking at these outlooks. So just looking at what's going on right now with ENSO and the El Nino. So this map on the left side shows the current sea surface temperature anomaly. So how warmer or cooler than usual is the ocean. And you can see that big red streak emanating from South America out into the Pacific. So that's a very, very clear signal of the El Nino. That blue box there is kind of one area that scientists track more specifically and index what the variance is there. And that's what I've plotted on the Right. So currently we're well into El Nino conditions, and actually it's persisted long enough where this is going to be classified as an El Nino event. We're coming out of several years actually of these La Nina conditions where it's been cooler than usual. So it'll be interesting to see how this does play out. We have been seeing this is the ocean part of the El Nino. We have been starting to see more resemblance of the atmosphere response to the El Nino. But again, it's not a big slam dunk, but the El Nino is there. These are the probabilities from the Climate Prediction Center of the El Nino conditions continuing through the next several months and seasons. You see very high probability, basically 100% all the way through the winter, and only starting to drop appreciably as we get into the late spring and into the summer. So the El Nino is here and it's going to be doing its thing. But this is the very freshest, latest outlook. The Climate Prediction Center just updated these outlooks this morning. They update them once a month, and so this is the outlook for December, January, February for the Southwest. Their latest update does show about 2/3 of Arizona into a slight tilt towards above normal precipitation favored. But if you look at the map on the bottom left side here, again, if you think back to what does a typical El Nino look like, and we expect wetter than usual across the southern tier, but that's not always the case. So they're seeing a couple of other couple of things here that necessarily cause them to tilt it a little bit different direction. So not a very clear signal as you get into New Mexico and Texas, but even for Phoenix here, that you see this green shading, that's still only a 35% chance of it being above normal. You still have a 32% chance of it being a drier than usual winter, or a 33% chance of it being a usual winter. So even though it looks impressive on the map and being the green, it's not a huge change in the odds. If we think about temperature, the latest update shows no clear signal for temperature if it's going to be warmer or cooler or a typical winter coming up. You see the pattern for the entire country in the small map in the bottom left, seeing tilt towards a warmer than usual winter is more likely across the northern part of the country. Maybe a more typical winter even, which is not a very common forecast that we see them push out. So again, thinking of this probabilistically, just kind of carrying this forward with the temperature, I made these little bar charts for each season. So the Climate Prediction Center does these outlooks for 12 seasons or 12 months, a full year into the future. So they're not showing any tilt in the odds and the temperatures all the way through the spring. But then once you start getting into the summer, they are showing these higher probabilities that the summer and into next fall are going to be warmer than usual. And that's really not too surprising because the warming signal is so strong, and it's highly unusual at this point for much of the Southwest, especially places like Phoenix that have a below normal summer. They essentially don't happen anymore. So that's kind of a wrap on what I have from the center and the atmospheric rivers and El Nino and the outlook. So I'll be happy to talk about anything else or take any questions that you, Aaron, might have, or anyone else.
Thank you so much, Paul. If anyone has any questions, you can go ahead and throw it into chat. I thought that was a very interesting discussion. Thank you very much for your time. It's interesting to see the CPC putting the seasonal outlook. I forgot to look at it this morning. I'm so glad you brought that forward. And a little bit of precipitation, but you look at statistically and you look at all of the different ways that we assess what's going on with an El Nino event. It can be a hit or miss kind of situation, especially when we're considering we had 3 La Nina winters in a row and 2 were very dry. And then what we had last winter was La Nina. So it can be that kind of hit or miss idea. Is there an idea for getting an atmospheric river seasonal forecast, just like what CPC does?
Our center is working on some of that stuff, and if you go to that sub-seasonal to seasonal forecast page, there is some different information on there. There's some work that's being done with IRI, which I forget what that stands for, but certainly trying to push the boundaries of, and there, when you're starting to look at those kind of time horizons, you're not necessarily forecasting atmospheric rivers themselves. You're trying to forecast the broader scale weather patterns that are conducive to atmospheric rivers forming. So it's kind of a knockoff effect on that. So if you can get the weather pattern right, then you have better chances of showing that the ARs are more probable. So that's kind of where the science is at this point on that.
Yeah, I mean, it's a great thing. When I was growing up and in undergrad and grad school, I didn't hear much about atmospheric rivers. So I'm so grateful for all of the information that's pulling forward the knowledge that we're developing. It's wonderful. I'm going to go ahead and stop the recording if I can find the correct location to stop the recording. There we go. And